So chapter 5 is thermochemistry. We're going to start talking about just general rules of what is energy, what kind of reactions release energy or absorb energy. Yes?
Yeah, I was going to ask if, is thermodynamics more of like the physics of...
A lot of these equations are from physics,
and
yes.
then thermochemistry is like reactions that take place that cause it?
So we're going to be studying kind of both. We'll study thermodynamics, which is a lot of the physics, and then we'll also study thermochemistry, which is how do we use those equations with chemical reaction. Yeah. But if you've taken a physics class, some of these equations should be reviewed. Yeah. So first of all, forms of energy. Hopefully some of this is review. The idea of kinetic energy versus potential energy. So what is kinetic energy? Energy that's doing what? Moving, right? Whereas potential energy is stored energy. So when we think of potential energy like in a physics class, we think of like the ball sitting on top of the hill has potential energy as a result of its position. Once that ball starts rolling down the hill, now it has what kind of energy? Kinetic. So in chemistry, when we talk about potential energy, we're generally talking about the energy stored within chemical bonds that are released when those bonds are broken or formed. But kinetic energy is still going to be the same. So our equation, first equation of this chapter has a lot of equations, so I highly recommend you making an equation sheet. That way you can keep track of which ones we use, versus which ones are just used to go into deriving a bigger formula. And also so you can make notes. Like some of these are very specific about what units are allowed and which units are not allowed. So this equation is energy, and the subscript K stands for kinetic, is 1/2 mu squared, where m is the mass of the object and u is its velocity. If you took a physics class, they probably had a v instead of a u. It's the exact same equation used the exact same way. It's just our textbook uses a u for velocity. So u is the velocity. Now these are in SI units. So SI units, we learned back in chapter 1. What is the SI unit for mass? Kilograms, good. So this mass right here must be in kilograms. If you're making an equation sheet, make a note. Must be in kilograms. Number one mistake on the test is to leave that in grams. U is velocity. So velocity is a speed. So it is going to be something over something, a distance over a time. So what is the SI unit for distance? Meters, good. What's the SI unit for time? Seconds, good. So here our SI derived unit for velocity is going to be meters per second. And that will give us our kinetic energy of the object. So hang on to that equation for just a minute, and then we'll come back and use it after we talk about another kind of energy. So thermal energy is the energy associated with heat. In chemistry, there's a couple of different energies we can study, but thermal energy is probably the biggest one we study because so many chemical reactions involve a transfer of heat, either absorbing it or releasing heat. So when we're talking about thermal energy, we're talking about that kind of energy. Now that is caused by what the molecules on the atomic level are doing. Their motion, their vibration, how they are moving around is going to change its temperature. Now we can't see atoms moving around, but we can monitor what they're doing thermally by the change in temperature. So one of these sections in this chapter is going to be all about measuring what's going on in the chemical reaction by measuring the change in the temperature of the surroundings. So potential energy we already talked about. It's the stored energy. So chemical energy is a specific kind of potential energy stored within those chemical bonds. I'm not going to sit here and read off the entire definition. You can read those on your own. Next kind of energy we're going to calculate is electrostatic energy. Electrostatic energy is the energy between charged particles. So in chemistry, there's two different situations where we could have charged particles. There's subatomic particles that are charged. What kind of subatomic particles are charged? Protons and electrons. Good. So this energy could be the energy between protons and electrons. Now, what larger things could be charged? Larger than a subatomic particle? Ions. So whether it's a monatomic ion like chloride, Cl-, or sodium, Na+, or a polyatomic ion like sulfate, SO42-. Charged atoms or charged molecules are ions. You can also have electrostatic energy between them. Now, when we do electrostatic energy questions here, we're not going to ask you to actually calculate the electrostatic energy like we did with the kinetic energy. Instead, there's this little funny looking symbol here, an alpha. What does that stand for? It's not equal, but it is what? Proportional. Good. This is proportional. So this symbol means it's proportional. So we're not going to straight up calculate what the electrostatic energy is, but this tells us that when one side of the equation goes up, what happens to the other side? It increases as well. When one side of the equation goes down, the other side goes down. So what are these variables? Q1 and Q2, these are the charges of the particles. Charges. So as the charges go up, what happens to my electrostatic energy? Does it go up or down? It goes up. Good. On the bottom, D is the distance between them. What happens as the distance increases? What happens to our electrostatic energy? Goes down. Good. Because you're making the denominator bigger, which makes the overall number smaller. So in general, with electrostatic energy, as you make the charges stronger, the force between them becomes stronger. Although it's not the same kind of energy, it's a little easier to picture this with the analogy of magnets. So if I have two magnets and I bring them close together, I feel attractive forces or repulsion forces depending on how I've aligned the magnets. That is very similar to what electrostatic energy is going to be. So if I increase the charges and the idea of magnets, I make stronger magnets, what happens to the force of attraction or repulsion I feel? Does it get stronger or weaker? If I use stronger magnets.
Stronger, yeah.
Much stronger, right? So it makes sense as I increase the charges that the energy would increase. What happens is I take those magnets and I increase the distance between them. I pull them apart. What happens to the attractive or repulsive forces I'm feeling?
It decreases.
It decreases. Good. It gets weaker. So that's why when you increase the distance, the force, the energy there is going to get weaker. So in these cases, because it's proportionality, I'm not going to ask you to calculate what is the electrostatic energy. I will give you two different scenarios and say which of these scenarios has greater energy. So you'd have to just compare them in that case. So kinetic and potential energy are interconvertible, meaning you can start with potential energy and then turn it into kinetic energy, just like with the ball sitting on top of the hill that starts rolling. Same thing with molecules. Chemical reactions that gives off heat takes that chemical energy, which is stored potential energy, and converts it into thermal energy. Thermal energy is kinetic because it is caused by those molecules moving around and vibrating, being in motion. So it's still the same idea. All right. Law of conservation of energy. This is the first law of thermodynamics. It states that energy cannot be created or destroyed. It can only be transferred or transformed from one form into another, such as from kinetic energy into potential energy, or potential energy back into kinetic energy. Or it can be transferred from one object to another. If I take a hot piece of metal and I put it on the table, it can transfer that heat from the metal into the table. That's a transfer of energy, but the energy doesn't just disappear. If I set that hot piece of metal on the table and I come back and check it out later and it's cooled down, that's not because that thermal energy disappeared. That's because it got transferred into its environment. All right. When I talk about the environment, I'm usually talking about the surroundings, so just some terminology. The system is whatever we're studying. It could be that block of metal. It could be a chemical reaction. But that is our system. The surroundings are going to be everything else. So when that block of metal, I set it on the table and it starts releasing that heat, what is absorbing its heat? The surrounding environment. So the table, but what else? The air. What about you guys? Are you absorbing any of its heat?
Yes.
Yes, a very small amount because you're far away, but yes, you are. The entire, unless we've done something to somehow isolate that piece of metal, the entire rest of the universe is going to be considered the surroundings. That energy goes out and it just keeps on getting absorbed outward, infinitesimally, infinitely, whatever. Keeps on going unless you have somehow isolated that system. So when we talk about heat, heat is that thermal energy. Again, it can be transformed into a different kind of energy or it can be transferred. And we're generally talking about the transferred in this class. It's being transferred between two bodies, from the metal into the table or the air or the surroundings. So heat, when we're talking about it, we're usually talking about that heat flow, the movement. We're not really usually talking about that piece of metal sitting there. It contains heat. We're usually talking about what its change in heat is. Is it losing heat or absorbing heat? How much heat was transferred? That's usually what we're measuring. And we'll usually measure that from a change in temperature. What's its change in temperature versus the change in temperature of the table? So when we talk about heat, we're generally talking about the heat change. How much is it changing? Where is it being transferred? What's absorbing it? What's releasing it? So thermochemistry, therefore, is the study of heat and where it's going, how much is going in those chemical reactions. All right. Endothermic versus exothermic. We've all heard these terms before, right? Endothermic versus exothermic. All right, so a big part of this chapter is going to be different ways you can tell whether a reaction is endothermic or exothermic. So we're going to cover two ways right here to tell, and then later we'll find other ways that we can determine if a reaction is endothermic or exothermic. So first of all, exo. If something is exo, is it going out or in? Out, right? Exo, think exit. It's going out. So exothermic means heat is going in which direction? Out of the system. It's being released by the system. So the process would give off heat. So one way of looking at this or determining this is if you're given a chemical reaction. For example, here we have the combustion of hydrogen that we did on Friday. Hydrogen plus oxygen turns into water vapor. That's what we did in the little test tubes in lab. When we did this, it also released energy. Now, that probably wasn't a whole lot, but if it was a larger amount, you would probably definitely notice that it would heat up because this is combustion. And combustion, fire, as we know, is hot. It releases heat. So if you have energy written as a product, the reaction is producing energy, then it is exothermic. So that's one way of telling. If you're given a chemical reaction and energy is a product, then it is an exothermic reaction. Another way is if you're given something called an energy diagram. This is an energy diagram. It shows the relative energy levels of the reactants versus the products. So here the energy is increasing. Up here I have the reactants are high energy and the products are at low energy. Law of conservation of energy, you can't destroy energy. So to go from high energy, our reactants, down to low energy, our products, that energy had to have gone somewhere. That drop in energy, that excess energy had to have been released. So when your reactants are higher energy than your products, that means you're going to release energy and it is exothermic. So that's the second way of telling. Endothermic is going to be completely the opposite. Now energy is going to be a reactant because the reaction is going to consume energy. And here on the energy diagram, our reactants are going to be lower in energy than the products. So it's going to have to absorb heat in order to go up to the higher energy products. So if I had a chemical reaction going on that was endothermic, and it's going on in a beaker and I'm holding that beaker, would I feel a temperature change in my hand? Yes. What would it feel like? Cold. It would start feeling cold. Anybody ever use those instant cold packs for like sports injuries, little bags? You shake them up. Yes. Yep. So that is an endothermic reaction. So when you shake it up, you're usually releasing, most of those cold packs are like ammonium nitrate and water. You release the water, it dissolves it. That's an endothermic reaction. So it absorbs heat. What is it going to absorb that heat from? Whatever you put it on, your hand, your ankle, whatever you're trying to cool down. So it's not putting cold into you. Does cold exist?
No.
No. It's just a lack of heat, or the loss of heat is the sensation we describe as cold. Just as darkness doesn't really exist, it's just the absence of light. Same thing. You can't put cold into an object. An object will start feeling cold because heat is being lost from it. So it's the transfer of heat, whether it's going in or out, determines whether or not it feels hot or cold. But it's still heat being either absorbed or released. All right, back to those equations. So here is our equation again for kinetic energy, 1/2 mu squared. Let's talk about units. We said that it has to be an SI unit, so that mass M must be in kilograms, and the U velocity must be in meters per second. So if we plug all this in, we end up with this unit, kilogram times meter squared per second squared. That is our SI derived unit for energy. We're going to call that a joule, J. So a joule is defined as 1 Newton of force times a meter. So it's got two parts to this. First, you have to apply force, and second, you have to move the object in order for you to have energy. So here, a Newton, where a Newton is a kilogram times meters per second squared, is the SI unit for force, so how much force you're pushing on something, times a meter, how far that object got pushed, tells you how much energy was exerted. So there's our SI unit for energy. Let's try this out. So this is two-part question. The first one's kinetic energy. The second part is electrostatic energy. If you're following along in the book, this is on page 190. So part 1, calculate the kinetic energy of a helium atom moving at a speed of 125 meters per second. I'm going to open up a blank slide so we have some space. So you have a helium atom moving at 125 meters per second. And the question is, what is the kinetic energy? Okay. Because this chapter is a lot of math and a lot of formulas, a lot of students, the question here is, I don't know which formula to use. Again, that's why it's really helpful if you make your own formula sheet, because right there on the formula sheet you can write, this is the formula for kinetic energy. If kinetic energy is mentioned, this is probably the formula. And that'll save you a lot of headache about what formula to use. So our kinetic energy formula, let's just go ahead and write it up to the side here so we know what we're looking for. 1/2 mu squared. And now let's see if we have these variables. M is the mass. Do I have the mass? We can determine it. Good, we can determine from that thing up there. So let's find the mass. Find the mass of what? Good, mass of a helium atom. And what unit do we need this in? Good, in kilograms. All right. Good question. How do you convert it? All right, so first of all, on the periodic table, what does it say is the mass of helium?
4 grams.
Yeah, 4.003. 4.003, and what unit is that? AMUs, or we could use what other unit? Avogadro's number's not a unit.
Like mass over 1 mole. What is it like?
Grams per mole. Good. You can use AMUs if you know what the conversion factor is between AMUs and grams. It's okay if you do, or you can use grams per mole. Everyone's calling out different numbers. I don't know. All right, grams per mole. But we don't want, so that is how many grams an entire mole of helium atoms weighs. But I don't want an entire mole. I just want what? 1 atom. So how many atoms are in a mole? Good. The big number, yeah. 6.022 times 10 to the 23rd, Avogadro's number. So what do I do with Avogadro's number here? Do I multiply by it or divide by it? Divide by it. So if this is for an entire mole, I just want for 1 atom, and I divide by that number, 6.022 times 10 to the 23rd. What's the unit on Avogadro's number? Atoms per what? Per mole. Good. Think dozen. A dozen is also a quantifier. A dozen has units of items, whatever you have, per dozen. It doesn't have, it's not 12 dozen, unless you're talking about 144, but that's different. So atoms per mole, which means that moles cancel, and now we have the grams of 1 atom. Should this be a big number or a small number? Incredibly small number. If you end up with a big number here, that means you did not put your denominator in parentheses. Where's my good calculator? I'm getting 6.647 times 10 to the negative 24. Sound about right? For those of you who are following along with your calculator. So now what's my unit? Where that extra dot came from. Grams. Now this is the grams, just one atom, so we can just put grams, because that's what we're looking for, the grams of one atom. But what are we still missing here? Kilograms. What do we still need to do with this number? Divide it by 1,000. So we still need to divide by 1,000 grams per kilogram. So the grams will cancel. The number should get even smaller. I know I should do this in my head, but I don't feel like it. So I know. 6.647 times 10 to, instead of the negative 24th, it's now negative what? 20. 1,000 is 10 to the what? Third. So we add 3, negative 27. And now we're in kilograms. So this is our mass. It goes in right here. Now we can plug everything into our kinetic energy equation. Kinetic energy is 1/2 of that mass. Oh, 2 is messing up. 1/2 kilograms. And then U is our speed. What is U going to be? 125 meters per second squared. Make sure when you're multiplying this out, only the speed gets squared, because only U is squared. So that square is just on the 125. Now we're expecting a huge number or a small number. Still small. I mean, this thing's moving pretty fast, but it's also just a one little tiny atom, and it's a helium atom too, second smallest atom we have. So this is still not going to be a huge number. It should still be a small number. I'm getting 5.19 times 10 to the negative 23rd. And what will be our unit here? 23. Joules. Good. Kilograms times meters squared per second squared will give us joules. So there is our joules. I don't like that too. I'm going to make it look prettier. 23. And that's the answer. I could have given you this question reversed. I could have said, calculate what speed a helium atom is going if it's got this much energy. Or I could have also asked you, what is the mass of an object that has this velocity and this kinetic energy? So any equation in this chapter, pretty much, be able to solve for any of the variables. Yes?
Do you know what the average speed of a helium atom is at STP?
Not off the top of my head, no. All right, any questions with this? Ready to try part B? All right, back to part B. Part B says, how much greater is the magnitude of electrostatic attraction between an electron and a nucleus containing 3 protons versus that between an electron and a nucleus containing 1 proton, assuming that the distance is the same in each case? Whew. A lot of words there. I'm a visual person, so I like to take those words and turn them into a picture, a diagram. So I'm going to draw these two scenarios and figure out what the relative energies of each will be. Change the color here. So first, we have an electron and a nucleus containing 3 protons. So I'm going to draw an electron here. And then over here is a nucleus. Now, if the nucleus has 3 protons, what is the charge on that nucleus? Plus 3, or 3 plus. Whereas this electron has a charge of what? 1 minus, or minus 1. Doesn't really matter which one you do, for this case at least. Minus 1. And then it's separated by some distance. I'm just going to call that d. So that's the first scenario. Second scenario is an electron and a nucleus containing 1 proton, and the distance is the same. So again, we have an electron over here, same distance, and over here our nucleus has just 1 proton, so what's its charge? Plus 1. So the distance between these things is the same. The only difference is the charge on that nucleus on the right-hand side there. So let's look at our equation for electrostatic attraction. Equation for electrostatic attraction says electrostatic attraction is proportional to the product of the two charges, Q1 times Q2, divided by the distance. One more word I want to point out here, and that's the word right here, magnitude. What does the magnitude? What does that mean? Magnitude means like the size of it, right?
Yeah.
So does it matter whether we're going to get a positive or negative number?
No.
No. So if you had something that had negative 75 joules, what's the magnitude of energy? 75. Good. So by magnitude, that means we're going to ignore whether it's positive or negative. All right. Now let's go ahead and just plug in our numbers here. So for the first scenario, minus 1 and plus 3 are our two charges. So minus 1 times plus 3. And on the bottom is a distance. We're just going to leave that d for now. And the second scenario, plus 1 and minus 1 divided by d. Now because we're comparing these two, what can we do with that d there? Cancel it out. It's the same in both cases. So because we're just seeing which one's bigger and they both have d, we're just going to ignore d. Cancels out. So here, plus 3 and minus 1 gives us negative 3, which has a magnitude of what? 3. Doing that sideways things. Negative 3, which has a magnitude of 3. What do we have down there for the second one? Negative 1, which has a magnitude of 1. So how many times greater are we? 3 times greater. That's the answer, 3 times greater. Yes?
So would that mean that?
All right. So, units. Just like with volume, we have the SI derived volume. What was the SI derived unit for volume? Meters cubed. Meters cubed, right. But that's not a very useful volume. More useful volume is what? Liters. But here in the U.S., what unit of volume do we use instead? Gallons, cups, teaspoons, fluid ounces, quarts, pints, all that fun stuff. So the same thing with energy. We can have a unit of energy that is the SI unit that is used by majority of the world, and that's going to be joules. And then we have the unit we like to use here in the U.S., a more common unit. So our more common unit for energy here in the U.S. is not a joule, but a calorie. A calorie is defined as how much energy it takes to raise 1 gram of pure water by liquid state by 1 degree Celsius. But where do we usually hear calories used? Food, right? How much calories is in your food? How many calories did you burn running on the treadmill? That's usually what we're talking about. So those calories are calories with an uppercase C, and they're commonly called nutritional calories. So on this little slide right here, I'll change color here. The uppercase C calorie is sometimes called a nutritional calorie. Nutritional calorie, and it is technically a kilocalorie, or 1,000 little calories. So when you look on the back of your thing of Nabisco cookies and it says that serving size has 280 calories, it's really 280,000 calories. Or it could take 1 gram of water and raise it by 280,000 degrees. A lot of energy there.
So I'm eating more calories than I actually think I'm eating.
Which is why we typically have these nutritional calories so we don't scare people away. But in the countries, like in Europe, where they use joules instead, the nutritional facts, instead of having calories, will have joules or usually kilojoules written on the back. Yeah. It'll have kilojoules on the food, instead of calories. So the conversion factor we're going to use between calories and joules is 4.184 joules per calorie. So there's our unit conversion between calories and joules. All right. Ready to move on to section 2? Good. All right, that wasn't so bad. We only had 2 equations and 1 conversion factor in section 1. Not so bad. So let's move on to the beginning of thermodynamics, talking about state functions and those systems. So earlier when I was talking about our system, and I was giving the example of the block of metal that we put on the table and the entire rest of the universe was its surroundings, I kept on making the disclaimer, unless we somehow isolate that system. So when we talk about a system, the case of that metal sitting on the table is what we would call an open system, meaning that it can exchange anything with its surroundings. Now in the case of a block of metal, it's probably not going to change mass, but if I had, say, a beaker full of hot water in the same scenario, yes, it can release heat to the surroundings, but also hot water tends to do what over time? Evaporate, which means what will happen to its mass? It'll decrease. Now, is that mass getting destroyed? No. Just like energy is conserved, mass has to be conserved. So where's the mass going?
The atmosphere.
The atmosphere, going to the surroundings. So an open system would be like an open beaker sitting there, just releasing both the energy and releasing its mass into the surroundings. That's an open system. A closed system would be if I took that beaker and I covered it with parafilm. Now, can it release any mass into its surroundings? Well, we're assuming we're measuring the whole beaker. So it can't escape the beaker anymore. So now the mass cannot be released into the surroundings, but it can still release its heat into the surroundings. It can still change its temperature. That's a closed system. It allows the transfer of energy, but not mass. An isolated system does not exchange either mass or energy to its surroundings. So that's like if I took that beaker and I put it in a very, very good, very assumingly perfect insulation, and I measured it. Yeah. Some sort of like a vacuum insulated thermos. Yes, technically those things aren't 100% perfectly insulated, but it'll probably keep it hot for a long time. So that's an isolated system. Questions about those systems? All right, so next we're going to talk about state functions. A state function is defined as some sort of function where such as the I define state functions as anything that can be measured by the initial versus final state, and it does not matter how many steps it took to get there. It's only defined as the final state versus the initial state. So a state function that you're very familiar with is probably temperature. So let's go through a little scenario here of temperature. Let's say I start with an object, and initially that object is 25 degrees Celsius. And I'm going to take that object and I'm going to heat it up. Give me a final temperature. Not final temperature, but new temperature. 2,000 degrees Celsius, sure. Hopefully. Let's do 2,000. It'll probably melt, but I don't know. Maybe we have a diamond here. 2,000 degrees Celsius, sure. And then I let that thing sit there for a while, and I measure it again, and it now has a temperature. It has cooled back down, and it's at 75 degrees Celsius. For this object, what is the change in temperature? (50 degrees Celsius). Did this middle step matter at all in that? No. Apparently not. I could have gone straight from 25 to 75, and it would have been the exact same change in temperature. So change in temperature is a state function. It only depends on your final state and your initial state, regardless of how you got there. Whether you heated directly from 25 to 75, or in this case, heated up to 2,000, and then let it cool to 75, it doesn't matter how that was achieved. All that matters is your final function, your final conditions versus your initial conditions. So temperature is an example of a state function, and we'll measure a few other state functions this chapter. Yes?
Why didn't we use the high number if it didn't matter?
Because it does, I was pointing out that it doesn't matter.
So why did we use the high number?
Because I wanted to point out how much it doesn't matter. It doesn't matter how you got there. That's the point of a state function. It's like if you were measuring your difference in altitude. Say you're at a building that has, 50,000 stairs. I don't know. And you're measuring your change in altitude. And you start off at the ground floor, and you climb all the way to the top of those 50,000 stairs. And then you climb back down to where you're only maybe 100 stairs higher than when you started. And if somebody asks you, what's your change in altitude? Your change in altitude is 100 stairs. Doesn't matter if you climbed all the way to the top first. At that moment, while you're standing on stair 100, your change in altitude is 100 stairs. That's the difference in your height between the ground where you started and where you're currently standing. I feel like this should have been, that slide should have been earlier, right after we talked about functions, or right before, after we talked about systems. So here's our example of an open system that allows both the water vapor and the heat. So there's the open beaker, or in this case it's a flask. Put a stopper on it, can't allow the mass in and out. This is now closed. And this is some sort of an isolating material, insulation around it. Now what's that last one? A what system?
Isolated.
Good, isolated system.
It's isolated, there's no transfer of heat or anything to the
Yep.
outside environment.
No transfer of heat, no transfer of mass. It's completely isolated. Yes?
Would the core of a planet or star be isolated?
No, because it can still release heat outwards. Yeah. I'm not an astrophysics specialist, but I would assume it still releases heat outwards.
I'm trying.
All right. First law of thermodynamics again states that energy cannot be created nor destroyed. Therefore, the change in energy of the universe must be constant. So when we're talking about an open system, the change in energy of the universe is the sum of our system and our surroundings. Whatever we're studying, and then it's all of its surroundings is technically the universe. So delta U is the internal energy, or the total internal energy. Internal energy. It is the most encompassing form of energy that we're going to study in this chapter. It's total energy. So the change in total energy of a system has to be equal to the opposite of the surroundings. So if my system released 20 joules of energy, how much energy was absorbed by the surroundings? 20 joules. So that's what this is saying. The exact same amount, just opposite in sign. Because if one is releasing, it's going to be negative. If one's absorbing, it's going to be positive. Because total energy is a state function, just like temperature, we can define it as the final state minus the initial state. So that's all that's saying. Delta U is the final state minus the initial state. So what kind of energies go into that total energy? One of them is the one we've already been talking about, heat. Heat is one of the energies you can have in a system that can be either absorbed or released. The other kind is work. So work. A system can do work. What is work?
Work is, it's how much, it's basically
Force times distance. Good. It's another kind of energy. So if I take,
I thought it was force over time.
it's force times distance. So if I take this and I exert a force on it, I push on it, and it doesn't move, have I done any work?
No.
No. But if I push on it and it moves across the table, now have I done work?
Ah, yes.
Now I've done work. So work is the energy that's associated with moving something over some distance. I exert a force and I push it some sort of distance. That's work. So just like heat can be absorbed or released, work can either be done on a system or done by the system. So when a system does work on its surroundings, that's like if I'm the system, pushing that marker was me doing work on the system. Now, work done on the system, sorry, on the surroundings. Work done on the system by the surroundings would be like if my surroundings somehow pushed me, like gravity pushed me down and I fell down. That would be the surroundings doing work on me. Our total energy is equal to the sum of these two, where Q is heat and W is work. Yes?
I was going to ask if you could ever have like a really weird scenario where a system does work on itself.
So a system like moved itself, you mean?
Like a car.
Like, I don't know, yeah,
It's
like
like,
something.
Well, see, because the car isn't really the system, you really would be looking smaller, like what's moving it? Well, the combustion is moving the pistons. So the combustion would be your system, the pistons would be the surroundings in that case. So it's not like the whole larger system that we're really studying there. So we're going to calculate, so this is the next equation we're going to calculate. This is equation 5.3 on page 193. Calculate the total energy of a system as the sum of its heat and its work, where Q is its heat and W is its work. So these questions at first glance seem really easy. You just add the two numbers together. What do I mean by that? I mean, here's an example. Calculate the change in internal energy for a system that absorbs 188 joules of heat. So there's our Q. And does 141 joules of work. So there's our W on its surroundings. So change in energy is Q plus W. So it seems like you just add the two numbers together, but there's always a catch, right? Normally the catch is the units. This one, units aren't a problem because they're both in joules and we're being asked for it in joules, so we're okay. The catch is that heat and work can be positive or negative depending on whether or not the system is absorbing or releasing, doing the work, or having the work done on it. So if we summarize this out in a table, this table on top page 194 summarizes that if heat is absorbed by the system, you have an endothermic process, your Q will be positive. If heat is released, your Q will be negative. Now, the question is not going to say your heat is negative 25 joules. It's not going to do that for you. The question would say the system released 25 joules of heat. It's up to you to look at the words and go, oh, that means Q is not 25, it's negative 25. Now work, you have to really pay attention to the wording for work. If work is done on the system by the surroundings, then work, W, is positive. If work is done on the surroundings or by the system and or, depending on the wording, then your work is negative. So let's go back at our question here. The system absorbed 188 joules of heat. So is Q positive 188 or negative 188? Positive, good. The system does 141 joules of work on its surroundings. So is work positive 141 or negative? Negative. Negative, good. Want to really make sure you knew that was negative. Negative 141 joules. So before we add them together, we needed to do that, make it negative. So once we have the positive Q, our heat, and our negative W, our work, we can add up and get our final answer, which is 47. Which, the next page? That one? For which one? Work? Work done on the system by the... Yeah, you're right. How did that happen? Because this is the same PowerPoint. Should be. No, it's her PowerPoint that's showing up wrong. Don't know. All right, so how can a system, a chemical reaction, do work and move an object? So it's obvious with me doing work by moving this marker across the table, But it's a little bit tricky to think about a chemical reaction. I kind of touched on it briefly when I talked about the combustion causing the pistons to move. Same idea here. So here I have a reaction. Now, heat being released or absorbed, that's pretty easy to visualize. So we're going to focus more on the second pictures, which are the work pictures. So here I have a chemical reaction of some sort taking place inside of a chamber that has a piston that can move up or down. Now, in this case here, the first case here, this reaction causes the piston to move up. So the chemical reaction is pushing the piston. That is work is going to be done by the system on the surroundings. So will work be positive or negative? Negative, good. Here, the second reaction now, this reaction causes the piston to move down. Now, what caused the piston to move down? Was it the reaction or something else? Atmospheric pressure or gravity pushed that piston down. Is that the system or the surroundings? Surroundings. So in this case, the work is being done by the surroundings on the system. It's pushing down on our system. So in that case, work would be what? Positive or negative? Positive. So in the cases of chemical reactions, we generally talk about it as a change in volume. Some sort of change in volume is causing that. Either increase in the volume or decrease in the volume. So if the volume is being increased, that's work is going to be negative. If the volume is decreased, in the second example, the piston's pushing it down, that means work is going to be positive because it's being done on the system. All right. Next section, section 3, is enthalpy. So, next we're going to talk about another state function very briefly, pressure. We're not going to talk too much in depth about pressure because we'll cover it a whole lot in chapter 10 when we talk about gases. We'll calculate all sorts of things about it. But for thermodynamics, it matters whether or not our pressure is being held constant or our volume is being held constant because that's going to change our math here of our state functions. So here I have a chemical reaction. This is sodium azide. Sodium azide, when it combusts, blows up, it produces solid sodium and nitrogen gas. So it starts.
Sodium starts blowing up.
Yeah, well, yeah, solid sodium if you have enough heat there, depending on how much heat it produces. But mostly we're interested in the nitrogen gas. Now this chemical reaction is actually fairly common, hopefully not too common, but you may have encountered in your life. Most of you guys probably were within a couple of feet of sodium azide at some time this morning. It's commonly used in cars. Anybody know what sodium azide is used for in cars? No, it's not in the battery. Something that you want to, when it explodes, produce a whole lot of gas. So I go from a solid state to something that produces a lot of gas. What's that going to do if I don't have that under any sort of pressure? What would happen? Increase the volume. So what's something that in case of emergency I want to rapidly increase in volume? Airbags. Good. This is the compound that's used commonly in airbags to rapidly inflate them. A very small amount. Very, very small amount. But it's made in a bag full of nitrogen gas, which is inert. So, Inert meaning it's not going to react. There's no oxygen in there. There's no oxygen inside of the airbag for it to react with.
But if it did react, it might make it safer, because then it would be an oxide version.
Yeah. Well, nitrogen is pretty inert, but also these reactions, one of the reasons why this is a good reaction is it does not create a whole lot of heat. It does create some heat, but not a whole lot of heat compared to most combustions. Here in this scenario, though, instead of it being in an airbag which inflates, I have it in a volume that has a set volume. It's not going to expand such as an airbag or a balloon would. So when the reaction goes off, because my volume did not change, what happened to my pressure? It increased a lot because solids take up significantly less room than gases. Gases take up a lot of room. So if the volume is set and it's got nowhere to go, it's going to result in an increase in pressure. If instead I had this reaction with a piston, and that piston is exerting a set amount of pressure, and the pressure is now constant, when the reaction occurs, what will happen to the volume? It'll increase. Good. So very important to be able to do these calculations if you are manufacturing airbags, because you want that airbag to fill up exactly to the point where it is full without popping. You don't want to put too much sodium azide or it'll pop. You don't want to put too little sodium azide and have it not fully inflate and the person's head goes through the windshield. That's usually a lawsuit and a recall. You know, ask what are the Toyota. Yeah, Toyota. Yeah, my mom got a brand new car to that one. Yes. Be very careful. So as we said in the last section, when there is a volume change, that piston got moved up, work was being done by the system. We can calculate that as a property of the change in volume using this equation here. Work is equal to negative pressure times delta V. What's delta V? Change in volume. Uppercase V is volume. So the change in volume times the pressure can give us the work. Now, why is it negative? Good, because the system did the work on the surroundings. That's why the work is going to end up being negative here. Now, in this case, could I use this equation if the system was having work done on it by the surroundings? Could I use that equation? Yes, because then how would I get a positive number out of that?
Or actually, if the pressure would.
Pressure's still constant. In both these cases, the pressure's constant. But what would become negative to make overall the equation positive? Change in volume. Good. We said in the last slide that if the volume decreased, that meant that work was being done on the system by the surroundings. So if delta V becomes negative, the overall term becomes what? Positive. Good. Now, let's move on to continuing to talk about that delta U. We're going to take that first equation, delta U is equal to Q plus W, and we're going to plug in our new term for W, that negative P delta V. Now, when you have a state function that the math, the calculation depends on something being held constant, like this P delta V, in order for there to be a change in volume, what do we have to hold constant? In the last slide, what were we holding constant in order for this to work? Volume was changing, so that volume wasn't constant. What was constant? Pressure. Pressure was constant. So when we were writing out these equations, we have to specify that this only works when something is constant. We do that using a subscript. So here you'll see that this is a Q with a subscript of V versus a Q with a subscript of P. When you see a state function such as heat, with another state function as a subscript, the one in the subscript is the one being held constant. So that subscript V means that volume is constant. That subscript P means that pressure is constant. I point this out because I probably got through like 4 semesters of chemistry before anybody ever pointed this out to me. And I was like, well, that makes sense. I had no idea why some of these things had to be in subscripts before anybody pointed it out to me. So, and these are also all on page 196, 197. So we're going to go through deriving these. These equations are all equations that are highlighted and numbered. Therefore, they are showing up in your equation list at the end of the chapter. These are not equations, however, you're going to be calculating with. They are used to derive equations. So I caution against putting equations like this on your equation sheet. They're used to illustrate concepts, but you're not actually going to calculate anything with them. So some students get really confused by having that many equations. So if you're worried you might get confused, then just don't write down these equations. Just write down the concept behind it. So let's introduce a new state function. Uppercase H. Uppercase H is enthalpy. Enthalpy with the T, H, not to be confused with entropy, which we will cover later in chapter 19. Enthalpy is defined as the sum of U, your internal energy, plus PV, that pressure times volume, which is basically taking the last equation we had here and rearranging it so that we've solved for Q. So enthalpy goes hand in hand with Q. What was Q again? Q stood for what? W stood for work, Q stood for heat. Heat. So enthalpy is the state function that's defined as the heat value of a system, or its thermodynamic energy of a reaction. So for any process, because it is a state function, it's still going to be your final state minus your initial state. We could also have this at constant pressure. It's equal to delta U plus P delta V. These equations we will not be using this semester. If you go on to take higher level chemistries, you will be using lots of these. If you go on to take thermodynamics in a physics class, you will be using these equations more. But we're not going to use them more than for the concepts here. So again, if you feel confused by all these equations, just don't write them down. Just know the concept behind them. All right. This is summarizing down why at constant pressure, the change in enthalpy is the same as heat. At constant pressure, not constant volume. That's because in the thermochemical reactions we typically do here in the lab, we're at constant pressure because we're just usually atmospheric pressure. We're usually not constant volume, at least not in this lab. We don't have the equipment to increase or decrease our volume. We don't have vacuums in here, pressure chambers, so we're just going to assume constant pressure. So for our purposes for this class, when we're talking about the heat and enthalpy, they're just going to go hand in hand here because we're going to be at constant pressure. All right, so again, just know the general concept there. So for any reaction, because enthalpy is a state function, it's the final state minus the initial state. For a chemical reaction, your final state are your products. Your initial state are your reactants, right? So we could write the change in enthalpy as being equal to the enthalpy of our products minus the enthalpy of our reactants. And that's the same as the state function, final state minus initial state. So again, right now, that's just a concept. We will use that in an equation later on, right at the end of the chapter. But for now, this is just a concept as we go into thermochemical reactions. All right. So a thermochemical equation is a chemical equation that has one extra component, and that is your enthalpy term. So here I have CH4. What is CH4? Methane. Good. This is methane. In this reaction, methane reacts with oxygen to make carbon dioxide and water. What kind of reaction is this? Combustion. So it is burning, right? I have a delta H value of negative 890.4 kilojoules per mole. Now, if we think about enthalpy in terms of heat, constant pressure, it being negative, does that mean that heat is being released by the system or absorbed by the system? Released. So if this system is releasing heat, what happens to the surroundings? Do they go up in temperature or down in temperature? Up. Does this make sense? Fire hot, release heat? This should make sense. It should make sense when we think about it. This is releasing heat. So it's negative enthalpy. This is another way of telling if the reaction is endothermic or exothermic. So this reaction, endothermic or exothermic? Exothermic. So we talked about two ways at the beginning of the class to tell if it's endothermic or exothermic. Here's a third way. If your enthalpy term is negative, like this one, you are exothermic. You are releasing heat. If it was positive, then you would be endothermic, absorbing heat. What this is down here is saying is that this enthalpy term, because it is part of the equation, you can use it in a stoichiometric ratio or a molar ratio, just as another term. So in the terms of this equation, 890.4 kilojoules per mole means per mole of reaction. So I could write it in terms of moles of methane, in terms of moles of oxygen. Now, why do I have a 2 there? Because there's a stoichiometric coefficient of 2 in the equation. In terms of carbon dioxide, in terms of water, again, I have a 2 because there's a 2 in the water there. So all this is saying is I can use my enthalpy term in terms of molar ratios when I'm doing stoichiometry. Now, stoichiometry. How many steps are there to a stoichiometry problem? 3, right? Number 1, get to moles. Number 2, multiply by the molar ratio. These things down here are molar ratios. And then number 3, get back to whatever your desired unit is.